In the summer of 1959, a test pilot climbs into a sleek black rocket plane strapped beneath the wing of a bomber. It's one of the fastest machines ever built, a hypersonic rocket plane that would fly to the edge of space. An aircraft so extreme, its pilots would earn astronaut wings. It was going to unlock the secrets of hypersonic flight, but the program's push into the unknown would come at a terrible cost. By the early 1950s, American aviation had reached an invisible wall. Planes had broken the sound barrier, but beyond Mach 3, the science of flight became almost entirely unknown. Engineers had no data on hypersonic flight. Wind tunnels could only simulate conditions up to about Mach 3. Beyond that, researchers had to rely on theory, educated guesses, and small, uncrewed rocket models. But the United States urgently needed this data, because both the Air Force and NACA were planning vehicles that would fly at hypersonic speeds. Future warplanes, reconnaissance aircraft, and eventually spacecraft would all have to survive the extreme heat and forces of flying many times the speed of sound. The only way to truly understand these conditions was to build a manned aircraft that could actually fly there and bring back real data. What they needed was a flying laboratory, an aircraft fast enough to reach the edge of space, rugged enough to survive re-entry, and precise enough to collect meaningful research. But in 1954, nobody knew if such a thing was even possible. At hypersonic speeds, air friction would heat the aircraft's skin to over 1,200 degrees Fahrenheit, hot enough to weaken conventional aluminum. And at altitudes above 100,000 feet, the air would be so thin that normal flight control surfaces would become useless. Pilots would essentially be flying in a vacuum, needing some way to steer the aircraft using thrusters like a spacecraft. And then there was the question of how to even get the aircraft fast enough. Conventional jet engines were useless at these speeds. The only option was a rocket engine, which meant the aircraft would carry a limited fuel supply and have only minutes of powered flight. So in late 1954, NACA and the military issued a request for proposals for a hypersonic research aircraft. North American Aviation and Bell emerged as the two strongest contenders for the airframe. Bell proposed a delta wing design with a more conventional approach, but North American's concept was something entirely different. North American had built the legendary P-51 Mustang and the F-86 Sabre, two of America's most iconic fighters. Their new design was radical: a sleek, dart-shaped fuselage with stubby wings, an enormous wedge-shaped tail, and a revolutionary new heat-resistant material called Inconel X, a nickel-chrome alloy that could withstand extreme temperatures without losing its structural integrity. It was heavier than aluminum, but it would allow the aircraft to fly through searing heat that would destroy any other plane. In September 1955, North American's proposal was selected for development. Their design would be designated the X-15, and it would be powered by a new engine built by Reaction Motors, the XLR-99. It would be the first large throttleable, restartable rocket engine, producing 57,000 pounds of thrust. Engineers designed a 50-foot-long rocket plane weighing over 30,000 pounds that would be launched from the sky. To make this work, the X-15 would be carried aloft beneath the wing of a modified B-52 bomber and dropped at 45,000 feet. The pilot would then ignite the rocket engine and climb at a blistering rate, burning through its entire fuel supply in under 2 minutes. After burnout, the aircraft would coast on momentum, then glide unpowered back to a landing on the dry lake bed at Edwards Air Force Base. Because the X-15 would fly above the atmosphere, it featured a reaction control system using hydrogen peroxide thrusters to steer in the vacuum of space. At lower altitudes, conventional control surfaces would take over. The pilot had to manage both systems during a single flight, essentially transitioning from spacecraft to glider in a matter of minutes. At peak speed, aerodynamic heating would push temperatures beyond 1,200 degrees Fahrenheit. So, North American built the entire airframe from Inconel X, a heat-resistant nickel alloy that maintained strength at extreme temperatures. They also gave the X-15 an enormous wedge-shaped tail that provided stability at hypersonic speeds but had to be partially jettisoned before landing. Pilots wore full pressure suits, essentially early spacesuits, since the cockpit could depressurize at extreme altitudes, leaving them exposed to near-vacuum conditions. Capable of reaching the edge of space and returning with priceless research data, the X-15 was the most ambitious experimental aircraft ever designed. It would bridge the gap between manned flight and spaceflight. The first X-15 was rolled out in October of 1958, with North American test pilot Scott Crossfield chosen to fly the initial test flights. But the aircraft's revolutionary engine wasn't ready yet, so early flights used interim power plants. The first captive carry flight took place in March 1959, with the X-15 bolted beneath the B-52. The first unpowered glide flight followed in June 1959, with Crossfield successfully guiding the aircraft to a dead-stick landing on the lakebed. Then, on September 17th, Crossfield made the first powered flight, reaching Mach 2 on interim engines. The program was finally underway. But the road ahead would be far from smooth, because on Crossfield's second powered flight, one of the interim rocket engines exploded during ignition, blowing a hole in the fuselage and forcing an emergency landing. When the aircraft touched down, the nose gear collapsed and the X-15 skidded to a halt with a broken back. Crossfield walked away, but the aircraft needed months of repairs. On November 15, 1960, the much more powerful XLR-99 engine finally flew, and the X-15 leapt to Mach 3. But as the program accelerated, the extreme heat began warping panels and cracking windshields, and the aircraft's skin would glow cherry red during the fastest flights. Pilots pressed on, and the X-15 pushed into uncharted territory. But with each new milestone, the risks grew. In November 1962, NASA pilot Jack McKay was launched from the B-52 when his engine became stuck at only 30% thrust. He was forced into an emergency landing at Mud Lake, but his flaps failed and the aircraft flipped upside down, crushing McKay's spine. He survived, but the injuries would eventually force his early retirement from NASA. The damaged X-15 was sent back to the factory for extensive repairs. It would return as the modified X-15A2, longer and capable of even greater speeds. Despite the dangers, 12 brave pilots continued pushing the aircraft further. By the mid-1960s, the X-15 was routinely flying above 50 miles altitude, the boundary of space. Pilots who crossed that line were awarded military astronaut wings. Among them was a young NASA pilot named Neil Armstrong, who would later become the first man to walk on the moon. The X-15 was generating invaluable data on aerodynamic heating, re-entry dynamics, and pilot performance at the edge of space. Data that would directly feed into the Mercury, Gemini, and Apollo programs. In August 1963, pilot Joe Walker reached 354,200 feet, over 67 miles high, the highest altitude any winged aircraft has ever flown. And in October 1967, pilot Pete Knight pushed the X-15A2 to Mach 6.7, over 4,500 miles per hour, a speed record for manned-powered flight that still stands today. But as the program reached new heights, there were growing concerns about its future. The space race had shifted priorities away from winged spaceplanes toward expendable rockets and capsules. Plans had once existed to develop an orbital X-15 or use it as a testbed for a hypersonic scramjet engine, but funding was drying up. After the success of Mercury and Gemini, NASA's attention had turned entirely to Apollo. The X-15 program was gradually being wound down, with flights becoming less frequent and the remaining aircraft showing their age. But the program still had critical research to complete. And in late 1967, the flights continued, with new pilots and experiments, pushing the aircraft to the limits of what it could endure. On November 15, 1967, Air Force pilot Michael Adams climbed into the third X-15 for his 7th flight in the program. It was a routine research mission to an altitude of 250,000 feet, carrying several experiments. After launch from the B-52, Adams climbed to 266,000 feet, more than 50 miles high, qualifying him as an astronaut. But as he came over the top, something went wrong. An electrical disturbance had disrupted the flight control system. Without realizing it, Adams had drifted 15 degrees off heading. As the X-15 descended, the error grew rapidly. Within seconds, the aircraft was flying sideways at Mach 5. Adams radioed ground control that the plane seemed squirrely. Then came the chilling words, "I'm in a spin." No pilot had ever spun at Mach 5. Adams managed to recover from the spin, but entered an inverted dive. The aircraft broke apart at 60,000 feet. Major Michael Adams was killed. He was posthumously awarded astronaut wings. It was the only fatality in the X-15 program's 199 flights, and it effectively signaled the end. The X-15 was an engineering marvel, and while it never carried astronauts to orbit, it helped make the space age possible. Because the data it gathered on hypersonic heating, re-entry, and pilot performance at extreme altitudes fed directly into the designs of Mercury, Gemini, Apollo, and eventually the Space Shuttle. Its influence on aerospace engineering can still be felt today, and the Soviets attempted their own hypersonic research aircraft in response, but their efforts would remain largely unsuccessful and shrouded in secrecy.